Hello, today we're going to look at the strength of the nuclear force. The nuclear force holds the nucleus together, and in doing so it overcomes the Coulomb force, which is the force that acts between protons which are positively charged. And the Coulomb force is of course a repulsive force, so it's tending to push the protons apart and make the nucleus less stable. The nuclear force holds the nucleus together and is therefore more powerful than the Coulomb force. But what is the nuclear force? Well, you might think that it could be gravity, but it can't possibly be gravity for this reason, that the gravitational force would be equal to g times the mass of one particle times the mass of the other divided by the distance between them. Well, g is approximately 6 times 10 to the minus 11. The masses of, whether they be protons or neutrons, are of the order of 10 to the minus 27 kilograms. So that's 10 to the minus 27 times 10 to the minus 27. I'm only doing this in order of magnitudes. Divided by r squared. Well, let's say that the distance between a proton and a neutron is 10 to the minus 15 meters. Then r squared would be 10 to the minus 30. And ignore the numbers, let's just look at the order of magnitudes. You've got minus 27, that's minus 54, minus 11, that's 10 to the minus 65, divided by 10 to the minus 30, which is 10 to the minus 35 newtons. So the gravitational attraction between two protons, or a proton and a neutron, or two neutrons, that are separated by one Fermi, 10 to the minus 15 meters, is a measly 10 to the minus 35 newtons. Compare that with the Coulomb force, which of course will only act between two protons. Well, the Coulomb force is going to be Q1, Q2, where those are the charges on the protons, divided by 4 pi epsilon naught r squared. Well, again, the charge is 1.6 times 10 to the minus 19, so that's squared. That's Q1, Q2, because that's the charge on the proton. 1 over 4 pi epsilon 0, 1 over 4 pi epsilon 0 is 9 times 10 to the 9, which is almost 10 to the 10. And that's going to be divided by the r squared term, which again is going to be 10 to the minus 30. And if you again ignore the numbers, we'll call this 10 to the 10 plus 10 to the minus 38 is 10 to the minus 28 divided by 10 to the minus 30, which is 10 squared newtons. So 10 to the minus 28 over 10 to the minus 30 is 10 squared newtons, it's 100 newtons. So the repulsive Coulomb force would be 100 newtons. The gravitational attractional force is 10 to the minus 35 newtons. No hope. Gravity cannot be responsible for the nuclear force. Now we'll just pause for a moment and think, how do we know anything that we know about the nucleus? Well, you remember it all started with Rutherford's scattering. He sent alpha particles into a gold foil and observed how the particles scattered. Indeed, some of them even backscattered. And by looking at the scattering, he was able to make a deduction that the atom, far from being a kind of solid mass, which people had thought it was, consisted of a very small nucleus with orbiting electrons, and most of the atom was completely empty, which is why most of the alpha particles just went straight through, because there was nothing to stop them. The size, or the diameter of an atom, is of the order of 10 to the minus 10 meters. The order of magnitude of the diameter of a nucleus is about 10 to the minus 14 meters. In other words, the atom is 10,000 times bigger than the nucleus. So if you want to sort of scale this all up, if you represent the atom by the size of a room, the nucleus would be represented by a small grain of sand in the middle of the room. Now the next question is, how do we see anything that we see? The way we see it is that if I'm looking at another person, that light shines on that person and is reflected back to my eye, and that light has interacted with the person and comes back to me and reveals something about that person, the colour of the dress they're wearing or the colour of their hair, whatever it may be. But in order to do that, the wavelength of the light has to be of the order of, or very much less than, the thing that you're looking at. Now, light has a wavelength, ordinary visible light has a wavelength of the order of 10 to the minus 7 meters. So if you try to look at a nucleus with a wave of 10 to the minus 7 meters, there's the wave, the actual nucleus, the wave does not see, because the wavelength is just too big to interact with a tiny nucleus. That's why you can't see a nucleus with ordinary light. So if you're going to interact with a nucleus, you need to have a wave that has a wavelength that is comparable to the size of the nucleus you're trying to see. And de Broglie has provided us with a way of doing that, because de Broglie's formula, which I cover in a whole range of other videos on nuclear physics and on quantum physics, is that the momentum of a particle is equal to Planck's constant divided by the wavelength of a particle. In quantum mechanics, we regard particles not only as particles, but also as waves. And if they have waves, then they will have a wavelength. And what this formula tells us is that as momentum increases, so the wavelength decreases. And you need a low wavelength if you're going to observe something that's very small. So you need a high momentum. If you need a high momentum, you need a high energy, because energy is pc, the momentum times c, the speed of light. So from this formula here, it's pretty obvious that p is equal to E over c. And if I substitute in this formula and rearrange for lambda, I get that lambda is h over p, and p is E over c, so it's hc over E. And that's going to be 6 times 10 to the minus 34, that's Planck's constant, times 3 times 10 to the 8th, that's the speed of light, divided by the energy. Now, if I want lambda to be of the order of 10 to the minus 15 meters, then you will see that the energy will have to be of the order of 1 GeV. 1 giga-electron volt of energy. And usually you would use electrons. If you've got electrons with 1 GeV of energy, they'll have a wavelength of 10 to the minus 15 meters, and that will enable them to hit and explore nuclei. And that's one of the reasons why we have high energy physics. You need these high energies in order to get the small wavelengths, in order to explore smaller and smaller bits of the nucleus. So what have these scattering experiments told us? Well, Rutherford's scattering experiment using alpha particles has told us that an atom consists of a small positively charged nucleus and orbiting electrons. More scattering has told us that the nucleus consists of protons and neutrons. And now even higher energy scattering, which gives us even smaller wavelengths so we can penetrate to even smaller levels, tells us that if you look at a proton and a neutron, these are not fundamental particles. These contain things called quarks. And for our purposes, there are two, the up quark and the down quark. There are 4 others, which I describe in my video on the Standard Model, but we don't need to know about those for today. Suffice to say that a proton is made up of 2 up quarks and a down quark, and a neutron is made of 2 down quarks and an up quark. So that's the proton, that's the neutron. Those quarks are electrically charged. An up quark has a charge of 2/3 of that of an electron, but it's positively charged rather than negative. And a down quark has minus 1/3 of an electron, so that is negatively charged. And consequently, you can see that if you have 2 ups and a down, which is a proton, that will be 2 2/3 minus a third, that gives you +1. So that is why the proton has a charge of +1, whereas for a neutron, 2 downs and an up, 2 lots of minus a third plus 2/3 is 0. And that is why a neutron has no charge. But notice that the neutron does have charged particles within it. It's just that overall the charge is 0. But these quarks have another kind of charge. It's called colour charge, from which we get quantum chromodynamics. Now, as I said before, it has absolutely nothing whatsoever to do with what we understand in the classical world by colour. It is simply a means of labelling the kind of charge that exists. This is not an electrical charge, it's different, and it's been called a colour charge. And the colours are red, green and blue, and in any nucleon you get one of each. So you get a red quark, a green quark and a blue quark, or in the neutron a red quark, a green quark and a blue quark. And the point about these is that rather like electrical charges, like charges repel, unlike charges attract. So a red will repel a red, but it will attract a blue and a green. So consequently, because you've got 3 different colours inside a nucleon, that's the reason why that nucleon is stable and why the quarks stay within it, because each is attracting the other 2. If you were to try to put another red quark in there, then of course the existing red quark would repel it. So we've got stable nuclei. It's also the case that just as if you had something with a plus and a minus, that would net out to 0, it's also the case that a red plus a green plus a blue is effectively charge neutral. So once you've got a red and a green and a blue, you've got a 0 or a neutral colour charge. Now it is, and I'm talking very simplistically here, it is the colour charges, the reds attracting the blues and the greens and so on, that explain why the quarks are held together within the nucleon. That is the nuclear force. That's the nature of the nuclear force. What it doesn't, of course, explain is why there should be a nuclear force between nucleons. And to explain this, I want to go up to molecular level, and I want to consider the molecule hydrogen chloride. Now, the point about hydrogen chloride is that hydrogen has 1 electron, that's it, all it has. In its outer shell, chlorine has 7, 2, 4, 6, and an odd one. It essentially would like to have 8, and then it would be a complete shell, but it only has 7. So what hydrogen does is it kind of lends its electron to the chlorine, so that chlorine now has 8 electrons in its valence shell, its outer shell. But because hydrogen has, as it were, lent its electron, it is essentially net positively charged. And because chlorine has got a little bit extra, 1 extra electron, it is essentially negatively charged. So although the molecule as a whole of hydrogen chloride is neutral, it has a neutral charge, the bit towards the hydrogen atom is marginally positively charged, and the bit towards the chlorine atom is marginally negatively charged, which means that when another hydrogen chloride molecule comes up with this kind of dipole arrangement, it's a bit more positively charged on one side, a bit more negatively charged on the other, the negative charge here and the positive charge here attract, and you get a bond. It's one of the ways in which you get molecular bonding. Now, in the same way, but keeping it very simple, this is what happens within nucleons. You can get a red and a blue and a green, which from a distance simply makes a net 0 colour charge. And then you bring another nucleon, whether it be, these could be either neutrons or protons, or a neutron and a proton, and you have red, blue and green. The blue and the green here are close enough that they can do the same sort of thing as the hydrogen chloride did. This blue, if it were far enough away, would simply see a colour 0 charge. But But if it's close, it will see the green is slightly more close than the others. So there's a net charge, there's a net force between the blue and the green that is attractive. And that is called the residual nuclear force. Now, it is actually much more complicated than that. It involves the exchange of pions, and I have done another video where I deal with that in a little bit more detail. But in essence, I'm trying to show you how the nuclear force is binding the nucleons together. Now, experimentally, we can find out what the shape of the nuclear force is. And what I'm actually going to draw this in terms of what's called the nuclear potential. You will often hear people call about nuclear potential. What they mean is nuclear potential energy. I'm sorry about the camera keeping refocusing. I thought I had set it to fixed focus. I had done that and somehow it's now playing up. I shall have to check it later. But anyway, if it keeps fiddling around with its focus, that's the reason. Sorry. If you actually plot the nuclear potential, which is the nuclear potential energy, against R, which is the separation between two nucleons, the shape of the force, or in this case the shape of the potential, is something like this, where this is the negative side and is therefore the binding side, so it's the attractive bit, and this is the positive and therefore, as it were, the repulsive bit. So what this tells you is that when the two nucleons are very close together, almost touching, the nuclear force is repulsive, it repels, in order to stop two nucleons from crashing into and indeed merging with one another. But over the greater part of this bit here, you've got an attractive force. This is the force that's holding the nucleons together. But when you get out to a certain radius, R0, the nuclear force has pretty much fallen to zero. So beyond that, two nucleons do not experience a nuclear force. And we know that, actually, if I just call this not R0 but R is equal to R0 times a to the 1/3. We've done that in previous videos, that the radius of a nucleus is equal to a constant multiplied by the number of nucleons to the power 1/3, or the cube root of the number of nucleons. So let's consider the simplest attraction of all, which is the attraction between two nucleons. And we want therefore a stable atom that has just two nucleons, and that of course is a deuteron, which has a proton and a neutron, and that is essentially heavy hydrogen. That is its chemical symbol. It has one proton, it has one neutron, so it has two nucleons. And there is going to be a nuclear force operating between those two nucleons, and there's no other nucleons to bother about, so this is the simplest form. And we can measure experimentally. We can identify the binding energy of this deuteron, which I'm going to call minus 2.225 MeV, minus because it's a binding energy, it's an attractive energy, it holds the nucleus together. You would have to put 2.225 MeV of energy into the deuteron to get the proton and the neutron liberated. And the radius, R, capital R, is 2.1 Fermis, which is 2.1 times 10 to the minus 15 meters. Now, to try and calculate the nuclear potential, which is, remember, potential energy, I'm going to simplify the diagram I did on the previous page to a square well, where this is V, the potential energy, this is the energy at zero, this is the nuclear potential within the bit that is attractive, call that V0, that's the nuclear potential, and this distance here is R, which is 2.1 Fermis. So what we're saying is that the potential energy within the radius R is V0, and outside the radius R, beyond the radius R, the potential is 0. And what we want to know is, what is V0? Now, it's important to notice that V0 is certainly not the binding energy. The binding energy, it will turn out, sits somewhere up here. It's also negative, it's minus 2.225, but it's very, very much less in magnitude than the nuclear potential energy. This is the potential well, which is essentially creating all of the binding energy. Now, why is the potential energy not the same as the binding energy? Well, because we know that energy, which is in this case the binding energy, is equal to the kinetic energy plus the potential energy. And this is just the potential energy. So there's a kinetic energy term. We normally say that the kinetic energy is half mv squared. That can also be written as p squared over 2m, where p is the momentum and m is the mass, plus, and we'll just put v, which is the potential energy term. And classically, that is how you describe the energy, where, as I say, E would be the binding energy. But we have to now trespass into the world of quantum mechanics. And in my videos on the quantum mechanics playlist, you will find, I think the very first one I did, which was a simple derivation of the Schrödinger equation, shows how you can take this equation, p squared over 2m plus v, and convert it into the Schrödinger equation, which at its simplest says that h times psi is equal to E times psi. Now, what does this mean? Firstly, E is the energy. It's the binding energy. Psi is the wave function. In quantum mechanics, you do not regard particles as particles, you regard them as waves, so they have to be represented by wave functions. And H is what's called the Hamiltonian. It is not a number. You cannot say H equals E, because what H is it's actually a function. H is actually minus h bar squared over 2m. Second differential with respect to r, plus Vr, and that's H. So H acting on psi, that would be psi is equal to E psi. And I remind you that energy is the binding energy, which we know, but V, at least V naught, is going to be the nuclear potential energy, which is what we're trying to find. What is the depth of the potential well which is affecting this nucleus? Well, we're going to use this Schrödinger equation in two areas. We're firstly going to look inside the box, where V will be V0, because that is the potential inside the box. And then we're going to look outside the box, where V equals 0. So this term won't exist outside the box. So let's first of all do inside the box. So this is zone 1, as it were. Inside the box, I've got that minus h bar squared over 2m d2 psi by dr squared plus, and now inside the box V is V0, so it's going to be V0 psi equals E psi. And that means that d2, well, I better do it in stages, minus h bar squared over 2m d2 psi by dr squared is equal to E minus V naught psi. And I just put up a marker that both E and V naught are negative quantities. V naught has a magnitude that is greater than E. This is E here, the binding energy. But actually, both those terms are negative. So remember that they are negative. That will have a significance a little later on. And then I can do that d2 psi by dr squared is equal to, take this term on the other side, and of course you have to tip it upside down, so it's minus 2m over h bar squared into E minus V naught psi. Then I want us to consider that term there. And I want us to see that it is positive, right? It is positive because V naught is greater than E, so you might think that this would be negative, but since they're both negative numbers, you've got the equivalent of something like E is minus 2, and then V naught is something like minus 36. I'll prove that a bit later on. So that will be minus 36. So it's minus 2 plus 36 is plus 34. So this term is positive always because V naught is in magnitude greater than E, but they're both negative terms. So what I can do is to replace, I can say that d2 psi by dr squared is minus k squared psi, where k squared is simply this term in the box, and I've left the minus side on the outside. Now, this equation is not unlike the equation for simple harmonic motion. d2x by dt squared is equal to minus omega squared x. That is, acceleration is equal to minus omega squared times displacement. But the key thing about this is that the acceleration is always in the opposite direction to the displacement by virtue of this minus sign here. If the displacement is in that direction, the acceleration's in this direction, and vice versa. So this is a restoring force. As the pendulum or the spring or whatever is moving in one direction, a force is causing it to slow down and move in the other direction. But as it moves in the other direction, the restoring force is pulling against it again. So you get simple harmonic motion, which is, of course, wave-like motion. So what you get here is oscillations. So for our purposes, we had d2 psi by dr squared is minus k squared psi. And that means that psi inside the box, so it's psi in region 1, can be represented as A times sine kr plus B times cosine kr. That is the representation that will give you the oscillations. Now, I'm going to assume you don't believe me, so I'm just going to demonstrate that this is consistent with this. And the way I do it is I first differentiate once with respect to r. If I differentiate this with respect to r, I'm going to get Ka cosine kr, because when you differentiate a sine, you bring the k out and you change sine to cosine. But it's going to be minus Kb sine kr, because when you differentiate a cosine, it becomes minus a sine and you bring the k out. Now let's do it again. d2 psi by dr squared is equal to, you bring k again, but it's cosine to sine, so it's become minus k squared a sine kr. Then the sine to the cosine will just go, so it's going to be minus k squared b cosine kr. But if you take the minus k squareds outside, you're left with a sine kr plus b cosine kr, which is psi. So this is simply equal to minus k squared psi, which is what I've got up here. So that is entirely consistent. Right. This equation can be satisfied with a wave equation which is oscillatory. But before we move on, just remember something that we said, that when r equals 0, that is when the two nuclei are touching, when the two nucleons are touching, the force has to, as it were, be repulsive, or at least the wave function has to be 0. The wave function has to be 0 because you'll notice in other quantum mechanics videos that I've done, the wave function squared is a measure of the probability of finding that situation at that value of r. So what we're saying is when r equals 0, the probability of two nucleons having a separation of r equals 0 must be 0, the probability must be 0, otherwise they'd be crashing into one another, and therefore at r equals 0, psi must equal 0. So the probability of finding a separation of 0 is 0. Psi squared is 0. So if that's the case, then I can say that psi in region 1 is 0 when r is 0. Well, let's just keep this in. So I'm looking along this line here. When r is 0, sine of kr will be the sine of 0, and the sine of 0 is 0. So that's going to be 0, plus the cosine of kr will be the cosine of 0. Cosine of 0 is 1. 1 times b is b. So 0 equals b. And it's not too difficult to conclude from that b must therefore be 0. And consequently, psi in region 1 is simply a, which is some constant, times the sine of kr. So that's our wave function inside the potential well. Now let's look at region 2, which you may recall. I'll just quickly redraw the regions here. I was saying that this is 0, this is V0, and this is R. And we've just calculated the wave function inside the well. Now we're asking what happens when the radius is greater than capital R. What happens then? And that is going to be the Hamiltonian, which will say, let me just rewrite the Hamiltonian for you, minus h bar squared over 2m d2 psi by dr squared. Now it would normally say plus the potential, but the potential is 0, so we don't need to bother about that, and that equals E psi. Now if I just switch these round, I've got d2 psi by dr squared is equal to minus 2m over h bar squared E psi. Then I want you to look at that term in the box. That term in the box is positive, because E is negative, so minus times a minus is a positive. So that term is positive, so I can write that as d2 psi equal by dr squared is, I'll call that L squared psi. The reason I need this to be positive is that if I'm going to call that L squared, then L would, if this is positive, L will be real. If this is negative, L would be imaginary, and I don't want imaginary terms. So I've got a different situation to the one I had before. In here, I had the second differential was minus k squared psi. Here I've got outside the box that d2 psi by dr squared is plus L squared psi. Now this is not an oscillatory term, because this is not a restoring force. As it were, the acceleration is proportional to the distance. As the distance increases, the acceleration term either continually increases or it continually decreases, and it's exponential. So consequently, it's either going to go like that, or it's going to go like that, right? It doesn't oscillate. And the solution for that is that psi is equal to ce to the kr plus de to the minus kr. We've put both options in. This is the e to the kr term, this is the e to the minus kr term. And once again, I better prove that that is right. If I take d psi by dr, I'm going to get, the k will come down here, k c e to the kr, minus, because we've got a minus k here, minus k d e to the minus kr. Differentiate again, so we now get d2 psi by dr squared is bring the k down again. I've got k squared c e to the kr. Bring the minus k and the minus k, I'm going to get plus k squared d e to the kr. I've used k's here incidentally. I should have used l's because I've put an l there, but look, this is just in passing to prove it. And this is going to be equal to k squared into c e to the kr plus d e to kr, which of course is equal to psi. Actually, that's minus kr, sorry, that's a minus kr. So it's k squared into c e to the kr plus d e to the minus kr, which is psi. So it's minus k squared psi, although actually it should be L squared because I put L instead of k here. So I've just shown you that this is perfectly, this wave function is perfectly consistent with this solution here. I used k's, I should have used l's, but the point is made. So this is my wave function outside the box, but once again, so that's region 2, once again I can simplify this, because what do we know about psi squared? Well, I've already said, psi squared is a measure of the probability. It's the probability of the two nucleons having a particular separation. Now, nucleons must have some separation, so the total probability must add up to 1, because there's 100% certainty that the nucleons will have a particular separation, and 0 that they'll have anything else. We just don't know what it is. Therefore, psi squared can never be infinity, because if you've got an infinity, you can't normalise it to get 1. Therefore, this graph, this one, can't exist, because that goes up to infinity. The only one that can exist is the declining one. So this value, which is the ascending exponential term, goes, and you are therefore left with region 2 wave function equals dE to the minus LR. Put the L in now because it should have been L rather than K. So that's my wave function outside the box. So I've rewritten the two wave functions. Inside the box, just remind you what the box looks like. This is 0, this is V0, this is R. So inside from 0 to R there is a potential energy, potential well. You might call it a V0. We're simplifying because we're using a square well, which it isn't, but we'll go with it. Beyond R, V is 0. So the wave function in the well is represented by this term, the wave function beyond is represented by this term. Now, there are two more conditions that apply with wave functions. The first is that a wave function must be continuous. So if you're plotting the wave function against the value R, and here is capital R, what you can't do is to have a wave function which stops like that and starts like that. It has to be continuous, right? So it has to continue across the boundary, which means that the value of psi at this point is the value of psi inside the box and the value of psi outside the box, because the two are the same. Therefore, when R is capital R, psi 1 equals psi 2, because they are both at the same point. So A times sine k capital R, i.e. at the boundary, is equal to dE to the minus L capital R. Right? It's only at that point. Those two wave functions have the same value. The second thing is that the derivative of the wave function with respect to R must itself be continuous. That is to say, you can't have something that, if this is R, you can't have something where the wave function goes up like that and suddenly reaches a point and then just changes on a point. It must be a continuous, and the derivative must be continuous. So in other words, the derivatives of these two must also be equal. That is to say, the slopes of those two at R must be equal. So what is the derivative of A sine KR evaluated at capital R? Well, that will be KA cosine K capital R. That's the derivative. And here you're going to get minus L times dE to the minus L capital R. All right? So what we've said here is that the wave functions must be equal at the edge of the box, and the derivatives of the wave functions must be equal at the end of the box. In other words, the slope is the same if you look at it from either way. I'll call this equation 1, I'll call this equation 2, and what I'm going to do is to divide equation 2 by equation 1. So let's take the left-hand side. This divided by this is going to be, well, the A's are going to cancel, so that's just going to give me K times cosine of KR divided by sine of KR is the cotangent of KR. And on the right-hand side, this divided by this, well, that's just going to give me minus L. So that was fairly straightforward. Just to remind you that K was equal to the square root of 2m over h bar squared E minus V naught. And we satisfied ourselves that this was a positive term, so there will be a real square root. And L, we said, was the square root of minus 2me over h bar squared. And this is also a positive term because E is negative, so minus times a minus is plus. So we're going to get a real value for L. And you can substitute this value for K here and here. You can substitute this value for L here. And we know what R is. R, I told you earlier, was 2.1 Fermis. We also know what E is. E is minus 2.225 MeV. That was the measurable energy for the deuteron, which is what we are considering, the simplest case. What is the value of M? It's not simply the mass of the proton, because you've got a proton and a neutron, and what you actually have to do is to look at the centre of mass. And if you look at some of my classical mechanics videos, you'll see how centres of mass are determined. The actual value of M that has to be used in these equations is the centre of mass formula, the mass of the proton times the mass of the neutron divided by the mass of the proton plus the mass of a neutron. But look, hey, the mass of a proton and the mass of the neutron are so close, we might as well just call this the mass of the proton equal to the mass of the neutron. That's a good approximation, so I'll put approximately. It's a good approximation. This is mp squared divided by 2mp, and that of course is just mp over 2. So the mass you use is half the mass of a proton. So let's have a look at this. In this formula here, which is the one we've derived, that K cotangent KR equals minus L, we know R, because that's the 2.1 Fermis. In K, we know everything. The mass, we know h bar, that's Planck's constant. We know E, that's minus 2.225. We don't know V. That's what we're trying to find. With L, we know the lot. We know M, which is the half the mass of a proton. We know Planck's constant. And we know E, it's this value here. So we can substitute and find everything and get V naught. And if you do that, you will find that V naught comes out to be minus 36 MeV. So if I plot the square well representation that I was using, there is naught. This is now minus 36 MeV, and you can see that compared to that, the binding energy, which was minus 2.225 MeV, is very small compared to the nuclear potential energy, the nuclear potential well in which these two nucleons are sitting. And what you can see is that the deuteron is loosely bound. There are two nucleons. The total binding energy is 2.225 MeV, so that's very roughly 1 MeV per nucleon. Whereas you'll remember from the chart that was produced, when you get up to iron 56, which is the most tightly bound, that is of the order of 8 MeV per nucleon. So the nucleons in iron much more tightly bound than the nucleons in a deuteron. And as I said, psi squared is a proxy for the probability of finding the separation between the two nucleons at some value of r. It's a postulate of quantum mechanics. You can't prove it, but it works. So let's see if we can do that. First of all, let's see if we can work out what K is. K is the square root of 2m into E minus V naught divided by h bar squared. I did this on my spreadsheet, and I found that that comes to 0.9 Fermi to the minus 1. It must be Fermi to the minus 1 because, of course, you multiply K by R. R is a measure of length. K, therefore, must be a measure of inverse length, so that K times R is dimensionless. And then you can say that the sine of KR, when R is R here, 2.1 Fermis, that's going to be the sine of K, which is 0.9, times R, which is 2.1, and that's going to be 0.95, which means that's 95% of the let's put that there. Let's do it again. Sine kr is the sine of k, which is 0.9, times r, capital R, which is 2.1. And when you evaluate that, that comes out at 0.95, which is 95%. In other words, the wave function is 95% of its maximum at capital R. So if I draw the wave function against R, there's the wave function. There is R, the boundary of the square well. Oh dear, sorry about that. I'm plotting psi against little r. This is the value of r, 2.1 Fermis, and here the wave function has 95% of its maximum. At its maximum, of course, sine kr will equal 100%, and that will happen when kr is pi over 2. Right, sine 90 degrees, sine pi over 2 is 1, so that's 100%. And so consequently, kr must equal pi over 2. K we already know is 0.9 times r equals pi over 2. And if you evaluate that, you'll find that r is 1.74 Fermis. So if we plot psi against r, what we said was that at the value of r equals 2.1 Fermis, we're at 95%. And at 1.74, which is about here, we're going to be at 100%. And it's a sine wave. So in other words, the wave looks something like, if I can draw it properly, something like that. And it would continue to oscillate, bar the fact that, of course, we've now moved out of the potential well, and now psi 2 takes over, the wave function outside the box, which is the exponential term. So let's have a look and see what that does. Well, L, you'll remember, was the square root of minus 2me over h bar squared, and that gives you a value of 1 over L equals 4.4 Fermis. Why did I calculate, why did I calculate 4.4 Fermis? Because if you're looking at e to the minus kr, e to the minus lr, when r is 1 over L, you've got e to the minus L over L, which is e to the minus 1, which is 1 over e. 1 over e is about 37%. So what we've established is when r is 4.4 Fermis, the wave function is at 37% of its maximum value. So when r is 4.4, which is almost double this radius of 2.1, well, it's actually more than double, the wave function has got down to about a third of its maximum value. And it's gone down by an exponential decrease, which I'm not drawing terribly well. And it will continue an exponential decrease as r increases. So that is the value of psi. Psi inside the box, this is the edge of the box, psi inside the potential well is a sine wave, where its maximum is at 1.74 Fermis, and it's got down to 95% of its maximum by the time you get to the edge of the box. You then have the exponential wave function taking over, which by the time you get to 4.4 Fermis, I'll put that there, 4.4 Fermis, you're down to 37% of the maximum, but it continues to go beyond it. So if psi squared is a measure of the probability, then you can see that since this is psi, you've just got to square it. The maximum probability is that you will find the two nucleons, the proton and the neutron in the deuteron, at 1.74 Fermis apart. But you might find them 4.4 Fermis apart. There will be a value for psi here, and indeed you might find them even further apart than that. But the maximum probability arises when the distance is 1.74 Fermis.